Yes. Okay, welcome to the second lecture of the course about market clearing in the form of equilibrium. Let me first share my screen. Yep. Can you see the screen? Yes, good, good. Okay. Yep. So let's continue. Yesterday, just a second, sorry. Yes, like this, it's better. Okay, yesterday in the last lecture, we talked about market clearing as an optimization problem, but today we are going to talk about market clearing as an equilibrium problem. So I don't know how many of you already knows about equilibrium problem, but hopefully if you are not familiar with equilibrium problem, I hope this lecture will help you to understand, to get a good idea about equilibrium problems, and also how we can write market clearing problem as an equilibrium problem. Well, let's see. So some recap from the previous lecture yesterday. If you remember, we had two thermal generators and we had two elastic demands to prices. And yesterday we realized that, okay, if we clear them by hand or by GAMS or Julia or Python, this will be the production of the two generators and the consumption of two demands and the uniform market price if there is no network. Also, yesterday, we ended up to this simple linear optimization problem for market clearing. So it was our social welfare, utility of demand, the cost of generators in the social welfare definition, the consumption side constraints, the generation side constraints, and power balance equality, whose dual variable gives us the market price if we use uniform pricing scheme. But now I have a new question. The question is that you solved this market clearing problem, and now you told generator G1 you have to produce 100 megawatt, or generator G2 should produce, I guess it was 50 megawatt. So the question is that how can we know that these four players, market players or market participants, G1, G2, and D1, D2, how to know that they are happy with the market clearing outcomes and they would not deviate from the market clearing outcomes? How to know that if we schedule generator 1 at 100 megawatt, how to know that that generator will not deviate, for example, will produce 90 megawatt instead of 100? How to know that the market clearing outcomes, they are how to say, satisfying results for all market participants? Do you have any idea? Nuran said they are maximizing their profit, definitely. Mehdi said if the constraints are obeyed, the players should be happy. I'm not sure. Farzad said we need to be in equilibrium point. Exactly, we need to be in an equilibrium point. Priyanka said write their individual optimization problems. Exactly. Okay, thank you. So let's continue. Exactly. Let's develop one optimization problem for each market clearing problem. Sorry, for each market participant. No, Magyar, we are not going to talk about Corno model. Corno is not a competitive model. It's a way to model the strategic behavior of the players. It's not something that we are going to talk here. So we would like to write one optimization problem for each market participant. So we have two types of participants, generators and elastic demands. So what is the objective of each generator? Maximize profit. Exactly. Exactly. Thank you. A lot of good answers. Good. And what is the objective of each elastic demand? Maximize utility. Exactly. Maximize utility. Yes. So the generators, they are looking for, they are self-interested. They are looking for maximize their own profit. And in the same way, each demand is seeking to maximize her own utility function or utility. So the next question, for generators, you don't need to say like in a formulation form. How can we calculate a generator's profit? Let's say a generator is producing 100 megawatt. Its cost, and we assume that the offer price is the same as the cost, is $12 per megawatt hour, while the market clearing price is $22 per megawatt hour. So how much is the profit of this generator? 1,000, exactly. So 22 minus 12 times 100, it's $1,000. So it's the profit of each generator. So if we write, exactly. So the profit of each generator, it's its production level. Maybe, yeah, I can change the color. Yep. It's the production of each generator times the difference of market price and the generator's production cost. And in the same way, yeah, thank you, Alina. And in the same way, the utility or the utility of each elastic demand, it's her consumption level times the difference of her bid price minus the market price. Do you agree? Is there any questions so far? Good. Any question? Is it clear? Yeah, let's continue. So now we like to write one optimization problem for each player, for each participant of our previous problem. So for generator 1, we are trying to maximize its profit, which is its production value, or the production level, which is variable, times the difference of market price lambda and its offer price, which is 12. And we know that we have a technical constraint. The production level should be equal to or greater than 0, but should be lower than or equal to 100. And we have two constraints, upper and lower. So this is a dual variable for the lower constraint or lower bound, and this is a dual variable corresponding to upper bound. Any question? Is it clear? Very good. And in the same way, we can write a separate optimization problem for generator 2, exactly in the same way. The only variable for generator 2 is its production level, and the same way we have a technical constraint. We have also the third optimization problem for elastic demand D1, who again tries to maximize its utility, and which is the consumption of that demand times the difference of the bid price 40 minus the market price. And again, we have a technical constraint for that demand. And finally, we have a separate optimization problem for D2. So though we are clearing the market, but every single participant, they are looking for maximizing their own, let's say, payoff. Could be profit or it could be utility. So every player has its own objective. Very good question. Esnil asked, is lambda is known? Very good question. We will get back. Yeah, that's my next argument. So Esnel, I will argue that that's a good point. Yeah, thank you, Esnel. Maybe you can answer it. Market price lambda is a given value, treated as a parameter within each optimization problem. So for generator 1 to demand D1 and D2, the price here, it's given. So for given prices, for given values of lambda, they are trying to maximize their own profit or utility. But the question is that, is lambda given? Do we know already a priori the optimal value of lambda? Do we know it beforehand? No, we don't need. We don't know. So the question is that, how do these four market players, they contribute to market price formation? In addition to this four optimization problem, do we need extra condition, extra problem? Yes, yes, exactly. As Priyanka said, Farzad and Xiaodong, Eric, Akilas, yeah, we need extra condition. We need power balance condition. And the power balance condition, you remember it was this, right? But it's a condition. It's not an optimization problem, right? It's just a condition. It's a coupling constraint, exactly as Akila said. It's a constraint wherein we have variables from four different optimization problems. So this is a coupling constraint. It's a constraint that links these four optimization problems. So this is why we call it coupling constraint. Very good. But these four problems, they are optimization. That one is a coupling constraint. Is there any way that also we write this coupling constraint as an optimization problem? I will explain later why we like to write it as an optimization problem, right? But for now, just answer me mathematically. Is it possible to write this constraint as an optimization problem? So we have four optimization. We like to write to add the fifth optimization problem. Do you have any suggestion? How to equivalently write this constraint as an optimization problem? Makis said, minimize difference of generation to demand. Good. Yes, max the surplus. Okay, let me continue. But there are, I think you are answering correctly, but yeah, I'm not sure just. Yeah. What Nima asked, aren't these smaller optimization problems already integrated and taken into account in the maximization of social welfare, i.e. buyer and seller surplus? Anyway, Nima, we need to add to include power balance condition, right? I mean, otherwise, without power balance equality, the four optimization problems, they are separated. They are not linked at all. Okay, so from mathematical perspective for now, please answer me whether this constraint and this unconstrained optimization problem, are they equivalent? Farzad said yes, Raquel, yes. Goran, okay, Goran, I'll get back to that. Nuran, yes. Priyanka, Lagrangian relaxation. No, I'm not relaxing anything, Priyanka. So my question is whether this constraint and this optimization problem, are they equivalent or not? I'm not relaxing anything. Okay. I think Nima's question is, what is the difference between this approach and the approach from yesterday? Goran and Nima, you are asking a question that I will ask in 10 minutes. So please be patient. I will ask exactly the same question in 10 minutes. Yeah. So let me help. Yesterday you learned KKT conditions, right? So this is unconstrained problem. If we take KKT of this unconstrained problem, what it will happen? If I take the KKT of this condition, there is no constraint. The only variable is lambda, right? So the derivative of the objective function with respect to lambda equal to 0. So it will be PD1 plus PD2 minus PG1 minus PG2 is equal to 0. It's the KKT of this constraint. And as you see, it's exactly equal, is exactly the same as our constraint, right? So the answer is yes. Yes, this unconstrained optimization is exactly equivalent to this constraint. Any question? Do you agree? If you say a few yes, I'll be happy. Yeah, good, good, good. Okay, so this is so we had mathematical interpretation, but what is economic interpretation? What does this optimization do? How can we interpret this optimization problem? What are we trying to do here? Minimizing the difference of consumption and production times lambda, while lambda is a variable. We know that it's price. How to interpret it? Profit. Yeah, you can say that lambda, yeah, they are revenues. Yeah, you can say. Maybe simply, we can say that we are just trying to penalize any mismatch between the consumption and production, right? So this is the difference of the total production and total consumption. We like to make it 0. If it's not 0, we are penalizing it by lambda, right? It's one interpretation. But remember, this optimization problem at the end of the day is equivalent to our power balance equality constraint. Could the optimization not become negative? Remember, it's equality constraints. Also, you can make it minus, minus, plus, plus. It's fine. It's the same. Mathematically, it's the same, right? Good. Goran, is it clear? No, Hosna, we are not minimizing the market price. We are not minimizing. Even if you write it maximize, again it works because the maximize is minimizing minus of this. And if you take KKTs, it's again this, right? So we are not minimizing market prices. Okay. Is it clear? Is there any questions so far? Good. Let's assume that we have the fifth player in the equilibrium setup. Yeah, we will. And let's call it price setter. Let's assume, and this price setter is a fictitious player. I will argue that we don't have such a player in reality, and we will argue why. But so far, assume that we have some imaginary player, and we call it price setter. And the price setter's objective is to minimize or penalize the supply and demand mismatch. So this is the price setter who solves this problem. I will explain later why we are keen on this kind of optimization problem and not this coupling constraint. Jan said, I guess that what Goran asked is that if we get a negative value, it's a better solution because we are minimizing. A negative value for what? That's a part of the question that I don't understand. For the objective function. For here. Yes. I guess that what is that if we get a negative value, it's a better solution because we are minimizing. Okay, now I understood. Yes, but yeah, but we will never get a negative value for that because, as I said, if you take KKTs, at the end of the day, PD1 plus PD2 minus PG1 minus PG2, it will be equal to 0, right? So the P variables are functions of lambda. Yeah. Okay, let me continue. If still there is a question, I will answer, but I haven't explained yet the whole problem. So maybe, yeah, we will, I think I will answer your questions properly. So just skip your questions, we will see. So if you agree, I included the 5th optimization problem for price setter, and this is the optimization problem. So this is the question that you can answer. Can we solve these 5 optimization problems separately? So Nikolaus says no. Nuran says no. Raquel, no. Eric, no. Okay, maybe one of you. Yeah, exactly. Yeah, I think Nuran, you mean they are dependent, not interdependent. Yeah, they are. Yeah, okay, they are interdependent. Yeah, exactly. No, we cannot solve them separately because they are connected. They are linked. How they are linked? Because lambda in 4 optimization problems, they are parameters while it's a variable for the 5th optimization problem. And in the same way, PG1, PG2, PD1, and PD2, they are variables for 4 optimization problems while they are parameters for the price setter, right? So I'm not talking about iterative solution. I'm talking about solving all 5 problems in one shot. And as you see, we cannot solve them separately. We need to solve all of them at once. And so all 5 optimization problems are linked and should be solved together. This is why I have a blue layout. We need to solve these 5 problems together. And this is a game theoretic problem. This is an equilibrium problem. So an equilibrium problem means we have a combination of, or a set of optimization problems that they are linked and we cannot solve them separately. We need to solve a set of optimization problems together. We call it equilibrium problem. Or it's also a game theoretic problem because we have 5 players. Each of them, they have their own objective. They are interacted. Each of them, they solve their own problem. And at the end of the day, it's a game problem. We have to solve this game problem, this equilibrium problem, and to achieve the solution. Is it clear? Good. This is a specific problem. It's also known as competitive equilibrium because it refers to market economy. It refers to market clearing problem. So it's also, we call it competitive equilibrium. So if you in papers, you see the term competitive equilibrium, we are talking about market clearing problem as an equilibrium problem. Good. So discussion, a question. So we saw that we realized that it's a game theoretic problem. But what kind of game theoretic problem is it? Is it a non-cooperative game or is it a cooperative game? Nuran says it's non-cooperative. Sorry. Non-cooperative. Okay. I got a lot of answers of non-cooperative. Nuran said players have their own. Yeah, players have defended their self-interest. Yes, exactly. So this is a non-cooperative game. This is a non-cooperative game, not a cooperative game, because we have 5 players here. All players are self-interested. They are looking for their own objective to maximize their own profit or utility. So this is a non-cooperative game. They are not cooperating with each other. Okay. Can one of you please tell me what cooperative game is in one sentence? In what conditions these 5 players they are playing a cooperative game? Exactly. If we assume that we have 5 players, 1, 2, 3, 4, 5, and they are making a coalition, they are all together as a single person, they are minimizing or maximizing something. For example, all of them together, like a single person, they go and earn, for example, $10, right? So the cooperative game, it's about ex post redistribution. How to distribute this $10 after a posteriori among these 5 people to make sure that they will stay in the coalition. That's the cooperative game, which is not the case here. Here we have non-cooperative game because each of these 5 people, 5 players, they are maximizing their own profit. They didn't build a coalition. Very good. We will talk about cooperative game in lecture 4. Okay. I added here 3 very seminal papers that I really like them. One is from Lenoit Kontrovich from 1939. But the paper published in 1960. Then another paper from Paul Samuelson, and another paper from Kenneth Arrow and Gerald Debro. All of them, they talked about competitive equilibrium. So competitive equilibrium is not something new. And we learned it from, I don't know, 60, 70, 80 years ago. So it's not something new. And always when you work on this type of problems, good to know the first papers that invented this problem. And these 4 people, Katranovich, Samuelson, Arrow, and Debru, all of them, they got Nobel Prize in economics in different years. We have a question from Louisa, but what if players are in a community? If they are in a community, they are solving a cooperative game. But but if you're talking about energy community, I mean, it depends on the people. Are they would like to build a market, a local market, in a cooperative setup or in a non-cooperative setup? Okay, but usually when we talk about community, we are talking about implicitly we are talking about cooperative game. Sebastian said, with not everyone having all of the information. Were in cooperative game or non-cooperative?
That was a 2-part thought when I said they have a common goal, but not everyone has all the information. Yeah. That would be a cooperative game.
Yeah, in the cooperative game, well, we have different versions, but also we can think of cooperative game with asymmetric information. Also in non-cooperative game, you can think of asymmetric information. What happens if information of the people in non-cooperative game are different than each other? For example, assume we have uncertainty, but the way the people, they see uncertainty is different. then we end up to a non-cooperative game with asymmetric information or heterogeneous information, which is not what I'm gonna teach in this course.
What I mean by different information, though, is everyone has knowledge of their own optimization, but I don't have knowledge of your optimization. So
Yes.
kind of by definition, that's always the case.
Yes, 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 yes. That's the case in a cooperative game, yes. Good. Also, I would like to introduce two very nice books. One with energy flavors, complementarity modeling in energy markets. But if you like to learn more about gain and variational inequalities that I will explain, it's good to read this fundamental book from Fassini and Zhangxi Peng. Also, if you like to take courses, there's a short course by Prof. Stephen Gabriel from at NTNU. Also, Professor Uday Shamba, he visited us in 2019 and gave a 5-day course. It's about advanced game theory in energy systems. And all the videos are available on YouTube, so you can check it out later if you like. Okay, is there any questions so far? No. Okay, so we have an equilibrium problem with 5 players, 5 optimization problems. We cannot solve them separately. So if we find a solution to our equilibrium problem, if such a solution exists, we will call it Nash equilibrium problem, coming from John Nash, who contributed a lot to game theory, firstly based on his thesis at Princeton University in 1950, I guess. But what do we mean by Nash equilibrium point, which is the solution of our equilibrium point? It's a solution, it's a market clearing outcome under which no market participant, neither G1 nor G2 nor D1 nor D2 nor price setter, none of them, they can increase their profit or utility or their objective function by deviating unilaterally from the equilibrium point. It means that, for example, if in the equilibrium point, generator G1 produces 100 megawatt, if this generator decides to go for 99 or 101, if it's possible, then this generator will not gain, will not earn extra profit. If we have such a point that no one can deviate from that point to get extra profit, then we will call it Nash equilibrium point. Is it clear? Yeah, good. Nice. Okay, I would like to have some discussions here. Is our market clearing problem with 5 players, is it a Nash equilibrium problem, or is it a generalized Nash equilibrium problem? Is it NE or is it GNE? I don't know how many of you knows about these notions. I will explain it in a minute, but is there any of you knows about the difference of NE and GNE? Very good. So there are something new that you can learn now. Okay, good, good, good. I got a lot of no, so I'm happy. Okay, let me first talk about Nash equilibrium. Let's say we have 2 players, only 2 players, right? Yeah, Drake. Yes, yes, yeah, Jan and Drake, they gave right answers, but let me explain. Assume that we have 2 players. Player 1 maximize, or let's say minimize to be in the canonical form. The player 1 minimizes its own function. So the only variable of player 1 is x, but its objective function is a function of x and y. I will explain what y is. And the only constraint of this generator, of this player, is is a function of only g lower than or equal to 0. Okay, that's our first optimization problem. The second one, for the second player, is minimizing over y. Again, the objective function, this is not a square, it's a superscript. F as a function of x and y, and the constraint is g, it's not a square again, of y lower than or equal to 0. Okay, so we have two optimization problems. Are they linked? Is it an equilibrium problem? Is this an equilibrium problem? Yeah, we have a lot of yes. Good. Yes, this is an equilibrium problem because y is a variable for second player, which has appeared in the objective function of the first player. And in the same way, x is the variable of the first player, which has appeared as a parameter in the objective function of the second player. Okay. Here, as we see, sorry. Yeah. Just a second. Only objective functions of the two players, they depend on the decision of the other player. While the constraints, they just depend on the local decision of the players, right? So here, the constraints, they depend on just the local variable, the variable of the corresponding player, but the objective functions, they depend not only our own variable, but also the rival's variable. This is a Nash equilibrium problem because only our payoffs, our objective functions are dependent to others' decisions. Our feasible space, our constraints are independent of the decisions of the others. We call it Nash equilibrium problem. Okay. What about GNE? Can you imagine what GNE will be? So if we write GNE for player 1 is minimizing over x, f of x and y, g of x lower than or equal to 0. For the second one, minimize only over I. Instead of f, I say h, x and y. And the constraint is k of y is lower than or equal to 0. For now, it's NE. It's a Nash equilibrium. But if we add y here and x here, it means that not only the objective functions, but also the constraints, the feasible space, are dependent to the decisions of the rival. Now this is generalized Nash equilibrium. Is it clear? Yeah, good. So let me get back to our equilibrium problem. Yes. Okay, Sergey, I will provide another. Yeah, that's exactly my question. This is our problem. Is it GNE or is it NE? Is it Nash equilibrium or generalized Nash equilibrium? Okay, we are converging to Nash equilibrium based on the answers in the chat box. But at the beginning, we had a few GNE. Also, we have AH. It's a Nash equilibrium, right? Because for generator 1, the constraints are only dependent to the local variable. The same for G2, the same for D1, the same for D2, and the same for price setter, because price setter doesn't have any constraint, right? We will talk about transmission constraints later, Tomasz, right? So this is Nash equilibrium. And this is why I wrote the coupling constraint as a form of price setter, just to clarify that the competitive equilibrium is a Nash equilibrium. It's not a generalized Nash equilibrium. Okay? Very good. So it's not a generalized Nash, it's a Nash. So back to back to our question. Is it a Nash equilibrium problem? Yes. Is it a generalized Nash? No. What is the difference we talked about? Which one is more appealing? The Nash equilibrium is always more appealing because under some conditions, we can argue about existence of the solution, the uniqueness of the solution. We have a lot of good properties in Nash equilibrium, but in generalized Nash equilibrium, we lose those properties. We can't, unless in very specific problems, we cannot talk about the uniqueness of Nash equilibrium problem, sorry, Nash equilibrium point in generalized Nash equilibriums. Okay, that's why, yeah. I talked about, okay, I'll finish in 4 minutes, then we will have a 10 minutes break. Let me write again the generalized Nash equilibrium. So we have minimize over x, f of x and y, g, x, and y is lower than or equal to 0. The other one is minimize over y. Let's say k of x and y. The constraint is h of x and y is lower than or equal to 0. This is G and E, right? Just for your information, if I make H G, is it still a generalized Nash equilibrium? So the constraints are common. Is it still a generalized Nash equilibrium? Yes. It's a G and E with shared constraints. It's a very common type of G and E's that we may have some properties there. But if you replace it G with H, then it's purely generalized Nash equilibrium. And usually we don't have much properties there. So if you're interested about GNEs with shared constraints, you can read some seminal papers from Patrick Harker. And he explained some conditions, which is now known as Harker conditions. And there we realized that for generalized GNEs with shared constraints, we may have a Nash equilibrium whose solution is the same as the solution of GNE with the shared constraints. Okay, but there are some certain conditions, and for that you need to read Harker's paper. Hope it's clear. Okay, just let me answer a few questions, then we can have a break. Prabhat, can you differentiate NE and GNE with payoff matrices? I think it would help my understanding. Well, it will open another discussion if we talk about the payoff matrix. But just for your information, in Nash equilibrium, only payoffs are dependent on the decision of rivals, on other players. But in GNE, not only the payoff, but also the constraints, the feasible space, are dependent to the decision variable of the rivals of other participants. That's the difference of NE and GNE. And remember, we have a very specific case of GNE. If the constraints are dependent to others, but those constraints are duplicated, are exactly the same, then it's GNE with shared constraints. Yeah. Peter, there must be some demands on the objectives that guarantee equilibrium convergence. If you're talking about regularizer, yeah, if we solve, okay, you're talking, Peter, about how to solve equilibrium either in a one shot, that will be the case for this course, or iteratively. Yes, in the case of iterative solution, we need a regularizer. Yeah, we will talk about it later. Good. Any other question? Okay, I suggest that I hold recording. Okay, let's continue. There was a question about Nash equilibrium of our problem. Why is it Nash equilibrium? Let me explain again. Here, lambda is a variable of another participant, which is price setter, but only appeared in the objective function of G1. The constraint of G1 only includes the internal decision variable of G1. The same for G2, lambda only appeared in the objective function, not in the constraints. The same for D2, D, and D1. While for the price setter, there is no constraint at all. And the decision variable of others only appeared in the objective function. So for all players, all constraints are independent of the others. They are just dependent on the decision variables of the corresponding player. This is why our problem, our competitive equilibrium problem, is Nash equilibrium, not GNE. There are a couple of questions. What will happen if we add transmission lines? I'll explain it later. I have a slide for that in later slides. We will see with transmission lines, again, it's Nash equilibrium. We will see. Is there any other question? No? Okay. I continue. Remember, at the beginning of the lecture, I had a question, how to make sure that when we clear the market using our optimization problem, the model we had yesterday in the previous lecture, how to know that every single participant, they are happy with the market clearing outcome. So yeah, it was our initial question. So still, we have to answer to that question. So I have another question now, an additional question. Now we have two forms of market clearing: optimization problem, as you saw yesterday, and equilibrium problem, as we talked about it today. So we have two forms of market clearing problems: optimization and equilibrium. So which one do we prefer? Which one we should choose for clearing a market? Optimization or equilibrium? Any answer? Priyanka says optimization. But what about equilibrium? Adam says it doesn't matter. Sebastian says for true market clearing, equilibrium. Jan again says equilibrium because there is no reason to deviate. Babu says maybe both. Akila says, I guess a TSO would do optimization. Nima says, does it depend on if we want to consider game theory or not? No, I mean, the question is that now we have two tools for clearing a market, optimization and equilibrium. Well, what should we do? Tomasz says, isn't the result the same? That's a good question. Raquel also says, is it the same? It is the same, question mark. Yeah, we will see. Hosna says, not all of the participants can solve optimization problem. I'm not talking about the practicalities, which one is harder or easier to solve. My question is more conceptual. Which tool we should really use? So Mahir says we have to use both of them. Okay, I think I got enough answers. So let's see. Okay, good. The other question is that how can we solve an equilibrium problem? That's the other question. We have 5 optimization problems. They are linked together. How are we going to solve it? Any clue? Akila says duality. Yeah, iteratively could be a solution, but let's say we would like to solve it in a single shot. Yeah, Sahan says KKT conditions. Abraham says the same. Yeah, Priyanka says the same. What do you mean by KKTs? As an MCP, exactly, Farzad. We have 5. Okay, let me continue the slides. Thank you. So we have 2 forms of market clearing. Equilibrium. Each generator has its own optimization problem. Each demand has its own optimization problem, and we have price setters optimization problem. This is what we learned today. Yesterday, we learned another form of market clearing in form of optimization, that we maximize social welfare subject to all technical constraints of generators and demands, as well as power balance equality. So the question was, which one should we use? So let me first check equilibrium. Some of you answered how we can solve equilibrium. Yes, what can we do is we can replace each optimization problem by its corresponding Tucker KKT conditions. So we can replace each optimization problem with its KKTs, replace this by its KKTs, replace this problem by its KKTs. Now we have a system of equations. There is no objective function here. It's just a combination of KKTs coming from different optimization problems, right? And what happens, now we have a system of equations, all the combinations of the KKTs. Now we call it MCP, mixed complementarity problem, and it's straightforward to solve it. For example, we can use solver path to solve it. We will see a code of paths in GAMS later in the slides. I also uploaded a paths code related to our example on DTU Insight portal. Carol asked, isn't optimization option cooperative? This one is not cooperative. Yeah, I will explain it. It's not cooperative. We will talk about that. But in cooperative, remember, all generators, all demands, they are building a single coalition. They go and maximize a collective, let's say, optimization, objective function. And then later they fight how to distribute the benefit, the collected benefit among themselves. So it's not a collective game, sorry, a cooperative game. Yeah, Jan, if you don't like to use, or if you don't have a solver on MATLAB, you can use the trick I explained yesterday. You can define auxiliary objective function, maximize one, a constant, and then you can solve your problem as a nonlinear optimization problem. Okay. Let's check again the equilibrium and optimization problems that we have. So we realized how we can derive an MCP from equilibrium problem. Also here, we have a single optimization problem, and we can derive KKTs, right? And I suppose we did yesterday. Good. So this is a question. Do the MCP, this MCP, and the KKTs coming from the optimization, do they include identical conditions? We have to check it. If so, we can say that the equilibrium and optimization problems are equivalent. It means that any solution to MCP also is a solution to KKTs of the optimization problem and vice versa. So what I'm trying to say that here we have an MCP problem. Here we can derive the KKTs. We can compare these two problems. If they are identical, if they are exactly the same, then it means that our equilibrium problem is the same as an optimization problem. Is it clear? So whenever you have two problems, either optimization, equilibrium, or whatever, and you have a question, are these two problems equivalent or not? Always derive the KKTs, compare. If you achieve the same set of conditions, then the original two problems, they are equivalent. Is it clear? You have equilibrium 1, equilibrium 2. Equilibrium problem 1, equilibrium problem 2. Are they equivalent? Derive KKTs, check. If the KKTs are equivalent, are identical, then those two problems equivalent. Or you have one optimization problem, one equilibrium problem. Are they equivalent? Again, we check their KKTs. If the KKTs are identical, the original problems are equivalent. Good. Let's check it out. This is our our equilibrium problem, right? With 5 players. Let's derive the KKTs. Let's start with this one. Is it in the canonical form? Is it in the standard form? Is this optimization? No. Okay. So we can write first in the standard form. So it's minimization over PG1, 12 minus lambda. So I multiplied by a minus, and then I changed maximization to minimization, subject to PG1 minus PG1 is lower than or equal to 0, and its dual variable is mu underline PG1, and PG1 is lower than or equal to 100, its dual variable is mu G2. Sorry, mu G1 upper line. Okay, is it in standard form right now? Yes. Now we like to derive KKTs, right? Remember, first we need to derive the Lagrangian function, which is a function of PG1, the primal variable, and the dual variables are mu G1 underline and mu G1 bar, which is the objective function minus mu G1 PG1 plus mu bar G1 PG1 minus 100. Do you agree? Yes. Good. Now if we take the KKTs, first we need to derive the derivative of Lagrangian function, with respect to the only primal variable we have, which will be 12 minus lambda minus mu g1 underline plus mu bar g1 is equal to 0. Do you agree? Then our equality, we don't have any equality. We have only inequalities. So pg1 minus is greater than or equal to 0. Mu g1 underline is is greater than or equal to 0. And we have complementarity conditions. Also, the other inequality, 100 minus pg1 is greater than or equal to 0. Mu bar g1 is greater than or equal to 0. And we have a complementarity condition here. So this is the KKT conditions of the first optimization problem. Do you agree? Very good. Nice. So in the same way, we have to derive the KKTs of the other 4 optimization problems, which will be this. So this is what we exactly obtained. Also, you can derive the KKTs for the other 4 optimization problems. As you see, this is our power balance equality. Also, we have to write here KKTs. Good. So now this is our MCP problem, our MCP mixed complementarity problem. So to solve this equilibrium, we need to solve this MCP problem. Okay. So this is why we need to learn how to derive KKTs. It's important to learn by heart how to derive KKTs. Brian said, if the following statement correct, if all the optimization problems of the generators and consumers are convex, then the MCP has a unique solution. No, let me explain. I'll talk about the uniqueness of equilibrium solution later in the exercise. I'll talk about that. But what you said, no, it's not necessarily correct. Who is solving the problem? That's a really good question. Sebastian asked, who is solving the problem? Who is solving an equilibrium problem? Sebastian asked, if it's central, why not just do an optimization problem? No, price setter is not solving the problem. Price setter is one of the players. So price setter cannot solve this problem. I would say someone like God, someone who sees all the, no single player solves the equilibrium problem. The equilibrium problem, by equilibrium problem, we can understand the interactions of different players. So for example, a market regulator or someone who sees all the interactions of players, that's the person who will solve the equilibrium problem, right? Yeah, I agree, the market operator or regulator. I didn't say yet which model, optimization or equilibrium, we will use in reality. So just be a bit patient. We will talk about that. Yeah, Sebastian, you said why not optimization? I'll get back to your question exactly. That's also my question. We will get back to that point. Good. So this is our MCP problem. Question, is this MCP problem identical to the KKT of the market clearing optimization problem? Let's check it. This is our optimization problem that we learned yesterday, right? If we derive the KKT of this problem, is it equivalent to this or not? Please check it for a minute and let me know. So I'm repeating the question. This MCP came from equilibrium problem. Now we have optimization problem. We like to derive the KKT of optimization problem and to see if it's equivalent to the MCP or not. We have 5, 6 yes answers in the chat box. Is there anyone who disagrees? Is it clear for everyone that, Peter, 1F in optimization, yeah? The lambda in the first line of each equation participant. Yes. Peter, are you asking a question or giving an answer?
Sorry, can you hear me?
Yes.
Yeah, I was just giving the answer that that is the way that you can see it's the same, because all the rest is the same.
Yeah, I totally agree. Yes, if you take the KKT of this optimization problem, is exactly the same as the KKTs, as the MCP. It means that what we learn here, we learned that our optimization problem for market clearing is equivalent to our equilibrium problem for clearing a market. They are not two different problems. They are the same. They are the same. Very good. Okay, Sebastian, I would like to get back to your question. You have optimization option. You have equilibrium option. Both are equivalent. Which one you are going to use in practice?
Neither.
Neither?
Because the problem remains that at some point somebody has to solve this. Somebody has to know everybody's requirements. Somebody has to centrally know everybody else's optimization problem, and that's never going to happen.
This is happening right now, right? How
no,
the market is
I mean, there's a free market where everybody puts a bid and an offer, and that's it. They don't give constraints. So it's not action optimization. It's completely suboptimal the way it runs now.
Yes, you're talking mostly about European markets, Sebastian. Okay. Let me open a parenthesis here. The way we clear the market in Europe is different than the way we clear it. I mean, not we. The markets are cleared in the United States. In Europe, the generators, they submit complex bids. They are responsible for their own internal constraints. So their bids implicitly include the constraints. While in the United States, we have simpler bids. The generators, they submit their bids and also they submit their constraints, right? So in Europe, we are solving the market a bit in a very liberalized way, in a free way, but in a bit complex way. But taking it aside about how we clear the market in Europe or United States, assuming that our bids, it means that all generators and demands and transmission lines, they share their information to a central player, say market operator. So then with that assumption, the question is that which one is easier to solve? And the answer is optimization problem. So this is why in reality, we are clearing the market using an optimization problem, not equilibrium problem, though they are equivalent. But solving a linear problem, optimization problem, is way simpler than solving an equilibrium problem that for that we need to derive KKTs and solve an MCP problem. For market clearing problem, always optimization and equilibrium, they are equivalent. But under some conditions, for example, if we call it externalities. If we have market externalities, then, for example, strategic behavior is externalities, or subsidies could be externalities. If we, how to say, we add externalities to market, if it happens that the optimization and equilibrium, they are not equivalent anymore, then we say that we have market failure. So market failure is a term that under some conditions, for example, from market externalities, the optimization problem has not anymore have equivalent equilibrium problem. It means that if there might be some generators or demands that may like to deviate from the market outcomes. If it happens, then we can say we have a market failure. But in our setup, which is everyone, it's a perfect competitive market, everyone offering their true cost, true utilities, there is no externality, then yes, optimization and equilibrium always they are equivalent. Externality is one example of international power exchange. Yeah, Makis, you're asking a question that we are deviating a bit from the content. The most important thing is that fundamentally in a competitive market without externalities, always our market clearing optimization problem has an equilibrium problem. If under some conditions, it could be anything, we don't have any more equilibrium problem, it means that we have a market failure. So is it clear? Ian asked, externality is, for example, the international power exchange. I don't know. We have to check it, how it might be seen as an externality. Yes. But now you learned that optimization and equilibrium, they are equivalent. But at the end of the day, we are going to solve optimization problem. But knowing that they are equivalent, does it give us any insight? The fact that optimization problem is equivalent to the equilibrium problem, can we gain any insight from that? The insight is that although we are solving the optimization problem, but implicitly we are solving an equilibrium problem, and we know that no one will deviate from market clearing outcomes. So getting back to our original question, how to know that no one will deviate? So the answer is that as long as our market clearing optimization has an equivalent equilibrium problem, then no one will deviate. Okay? Hope it's clear. Exactly, as Adam said, it means that every market participant, they are happy with this optimization problem, with the outcomes of market clearing optimization problem. Exactly. It means that the market clearing optimization problem gives us a Nash equilibrium point. Very good, Babu. Good. So conclusions so far, equilibrium problem, optimization problems of the market clearing problem, they are equivalent because their corresponding KKTs are identical. Both equilibrium and optimization forms of the market clearing obtain the Nash equilibrium solution. It means that there is no market player who desires to deviate unilaterally from the market clearing outcomes. So it's enough that we solve optimization problem for market clearing because we know that it provides us a Nash equilibrium point. Is it clear? Very good. Yeah, we have 5 yes. Is it, that's the only, I mean, what for others? I mean, is it clear for everyone? Good. Yeah, Very nice. Yes. So this is the optimization problem. Thank you. No, Ramin asked, does it happen also in GNE? I didn't talk about GNE here. Our market clearing problem here is Nash equilibrium. So you have to explain me how we can make our market equilibrium problem GNE. Then I can think of. What happens with ACOPF? That's what you have to check it out. With ACOPF, the problem is that the KKTs are not necessary and sufficient conditions for the optimality. But knowing that, still you can take KKTs and see what happens. My conjecture is that still the KKTs of equilibrium and optimization will be the same. Yeah, Yanis asked, is that applied if you are clearing a market with more than one bidding zone? I guess so. I guess so. As long as we are not adding some reasons, some externalities that optimization doesn't have anymore an equilibrium problem, it's fine. But you have to check each specific problem separately. So if you have an optimization problem, either in a zonal way or whatever, you have to check to see if you have an equilibrium problem that everyone is happy with the market outcomes or not. If you don't have such an equilibrium problem, then it means that we have a market failure. About transmission, I'll talk in a minute. I'll talk in a minute about transmission and transmission congestion. Okay, this is the market clearing problem as an optimization problem that we learned yesterday. We are maximizing social welfare, the generation and production limits, the nodal power balance equalities, the transmission line constraints, and the reference node. So this is what you modeled in exercise 1. So this is how we are clearing the market, right? I mean, in the practice. As I said, in European and US markets, they are different in many ways. For example, in Europe, we don't model transmission system as it is in the day-ahead market. We have the zonal representation of the transmission system. Also in Europe, the generators, they don't submit their unit commitment constraints. It's implicit in the bits. While in United States, we have a transmission system in the day ahead. The transmission system is modeled, and also the bits are way simpler because the market operator is aware of the technical constraints of the generators. But let's say for a generic market, this is the way we can clear the market using an optimization problem. Louisa asked if it exists and it's not unique. Will the Nash equilibrium be the same in both problems? Okay, Louisa is asking about, again, the existence and uniqueness of Nash equilibrium. I'll talk about it, yeah, maybe in 15 minutes. Good. The second form of market clearing problem is as an equilibrium problem. Remember, form 1 and form 2, they are equivalent. We saw it by deriving KKTs. So now we have one optimization problem for each generator who are trying to maximize their profit. We have one optimization problem for each elastic demand who maximize the utility. We have price setter, which imposes power balance equality for each bus. But also we have now an extra player, which is transmission system owner, or yeah, it's transmission system owner. So in the next slide, yeah. So you are familiar with this box. You are familiar with this box. You are familiar with the last box, but not with the one for transmission system owner. So we will focus it to this box for transmission owner in the next slides. This term is known as congestion rate. So let me explain. We can assume the transmission system itself is a market participant, and it's a spatial arbitrator. It means that the transmission system owner, it buys power at a specific bus and sell it back at another bus. Let's investigate the objective function of transmission system owner. And also let me check the chat box. Maren asked about externalities. If there is externalities, the only way is that you need to solve your optimization problem, but you know that there is no equivalent equilibrium problem, and some players may deviate. That's what it is. If that's the cost of externalities, you may end up in market failure. Yeah. So how do you solve your problem? It's using optimization problem. Just you can expect that some players may deviate. Good. Let me explain about the transmission system owner's problem. Let me assume that we have a simple two-bus system, bus 1 and bus 2. Price here is lambda 1 and price here is lambda 2. And we are transferring power from bus 1 to bus 2. It's F1 to 2. So for a transmission system owner, with this explanation, what will be the profit function for the transmission system owner here? Can you help me? You can assume that the transmission system owner is an arbitrator who arbitrage between the nodes. The arbitrator buys power F at bus 1 at price lambda 1 and sell it back at bus 2. Assume that there is no losses, just for simplicity, sells it back at bus 2 at price lambda 2. Exactly. So the profit of the transmission owner here is lambda 2 minus lambda 1 F12, which is equal to lambda 2 minus lambda 1. Remember, F is beta theta 1 minus theta 2. Do you agree? If we have two bus, this is our profit. And this profit, we will call it congestion rent. Okay, that's the profit of transmission system operator. Very good. If there is no congestion, how much the congestion rent will be? 0. If there is no congestion, lambda 2 will be equal to lambda 1, so congestion rent is equal to 0. So transmission owner earns money if there is a congestion. It's interesting. Good. Here in a compact way, I wrote the objective function here like this. Let's check if for the same example, we can get the same expression. So Yeah, Mehdi, I will explain what we will do with this congestion rate. Good. Here, as n takes 1 and 2, right? In our example, we have 2 buses. So when n is equal to 1, then our objective function is lambda 1, b, theta m. M here is 2. So when n is 1, m is 2. So theta 2 minus theta 1, right? And when n is equal to 2, m is equal to 1. So it's lambda 2, b, theta 1 minus theta 2. And we have a sum, so we have their summation. So this becomes, I would like to get something similar to this. It's lambda 2 minus lambda 1, lambda 2 minus lambda 1, times b, theta 1 minus theta 2. So it's exactly the same as here. So what I'm trying to say that this is our congestion rate, which is the objective function of transmission system owner who acts as a spatial arbitrator. So let me check the chat box. So it makes incentives for transmission planner, no expansion to make congestion and get profit. Yep. Yep. So do you agree so far? So next question. Are you familiar with FTRs, financial transmission rights? Have you heard about that? No. Okay, FTR is a mechanism that it's prevalent in US markets, but not in European markets. And I tried to explain it very briefly that you may like the notion. So again, here we have transmission bus 1 and bus 2. Say here we have a generator, here we have a demand. But this line is congested, right? So what happens? For example, here, our demand can buy financial transmission right of this line, of the single line. Let's say that this demand bought the 100% of the right of the line. So what happens? So though the generator sells the power at price lambda 1, D2 pays at price lambda 2, which is higher than lambda 1. But if the demand buys 100% of the FTR of this line, then we will pay the demand back the whole congestion rent of this line, of the corresponding line. So what happened? So it means that the demand D, though there is a congestion, at the end of the day, will pay at the price of lambda 1, because the congestion rent will compensate the difference of lambda 2 and lambda 1. Okay? So the demand may like to buy financial transmission rights. For example, if you buy 100% FTR, you will get the whole congestion rent. If you get the 50% of the FTR, you will get the 50% of the congestion rent. Okay? But to be able to buy FTR, the transmission system owner develops an auction at the beginning of a year or a season and sells FTRs. And then the demand D or other demands in the same node, they participate in that auction developed by the system transmission system owner, and they compete and they buy FTRs. Is it clear? So at the beginning of the year, transmission system owner sells FTRs. Then the FTR holders, they gain the congestion rents that that we calculate over the year. Yeah, of course, FTRs is topology dependent. Yes. Yes, and for every single line, we have FTRs. But yeah, I wouldn't like to go deep, but we have different types of FTR. Gate, point-to-point FTRs. I forgot the other one, gate flow FTRs. So there are different types of FTRs, but what I'm explaining is the basic definition of the FTR. So now let me explain, or maybe you can explain me what the benefits of FTR are for the demands here and for the transmission system owner. Why it's a good idea to have FTRs. Yes, of course, Mehdi, if there is no congestion, so no one will buy FTR, definitely. So for demands, what's the point of FTR? Why a demand might be interested to buy FTRs? Exactly, Thomas said, hedging. So by buying FTRs, the demand here hedges his risks of being congested, of having the line congested and paying the power at a higher price. So for demand, it's good. It's like an insurance, exactly. What about for transmission system owner? Why transmission system owner might be interested of selling FTRs? What's the point for transmission system owner? Nicholas said revenue security, exactly. So at the beginning of the year, transmission system owner sells the FTR, so the transmission system operator is being paid upfront, which is good. It's a revenue security. So you don't care about what's going on in the year. You will be paid at the beginning of the year, which is good. There's also another reason for transmission system operator. Here, transmission system operator, when selling FTRs, now the operation of the transmission system is, then the transmission system operator doesn't care about the operation of the system over the year, because the congestion rent will be paid to the FTR holders, not transmission system operator anymore. So the revenue of transmission system operator is independent of the operation of the system over the year. Is it clear? Good. Well, I'll not go deeper than that for FTR. Just I like to give you some idea about what FTRs are. Okay, we are again late in time. Next question. We had some argument that adding transmission line may destroy the fact that our model is NE, not GNE. Now I added transmission system here with an extra box. Is it Nash equilibrium or generalized Nash? Our market equilibrium problem with transmission system, is it NE or is it GNE? It is NE. It's still NE. So having transmission system will not make our problem GNE. Unless in some specific problems that I don't know. But here, with this specific problem, still we have NE, though we have transmission system. Is it clear? And if you like, no, actually it's next slide. And this is the third form of market clearing. It's an MCP problem. If you derive KKTs of the optimization problem or equilibrium problem, you will end up to this MCP. And you can check it out later if these KKT conditions are correct or not. So what we learned today, the bottom line, optimization, equilibrium, MCP. For market clearing problem, they are all equivalent. Okay? And this optimization problem could be in the form of primal, or it could be in the form of dual. All four forms of market clearing, they are equivalent. Good. The fun part. Is there any questions so far? If not, I can explain exercises. Is everything clear? Maybe you can write a few yes. Good, good, good. Thank you. I have 4 exercises for tomorrow. I don't expect you to go and check all of them, but it will be fun that you spend some time and see what these exercises are. Actually, we answered the first exercise. We have 2 forms, optimization and equilibrium. Which one is more appealing to market operators? Which one is more easier to solve? And I guess you already know the answer. But the other 3 exercises, they are a bit fun, but you may need to read a bit. The first question is that to solve an equilibrium problem, we derive the KKTs and we solved all KKTs together. The question is that, can we avoid deriving KKTs and solve the equilibrium problem iteratively? Right, please think of that. Here I added some guide, some explanations, and I have some keywords like Tatanmo process and Walrasian auction. Maybe you can Google these keywords for tomorrow, and maybe you can explain tomorrow what these keywords are and how we can solve a competitive equilibrium problem iteratively without deriving KKTs. Sebastian asked about the difference of GNE and NE. For that, I suggest that you can read the complementarity book of Stephen Gabriel et al. Where is it? This book. Here you can read a bit more. In chapter 4 and chapter 11 of that book, you can read more things. That chapters may help you to read more about NE and GNE. No, Googling NE and GNE is not very straightforward. But Sebastian, if you tell me what you really look for about NE and GNE, maybe I can provide you more exact references. But that's something that you can send me an email and I can get back to you. But is exercise too clear? Okay, let me explain exercise 3. Yesterday we had an let me say other way. Today we derived a Nash equilibrium problem. I'm not saying GNE, I'm saying Nash equilibrium NE. How to know that our Nash equilibrium problem, how to know it mathematically, that our Nash equilibrium problem has an equivalent optimization problem. If you have an equilibrium problem in hand, you derive the KKTs, but then you have to guess, do we have an optimization problem equivalent to our equilibrium or not? Yeah, I know, Mahia, you can check KKTs, but by checking KKTs, how can you end up to an optimization problem? Right? So you have an equilibrium problem, you derive KKTs, or you end up to MCP. How to know that we have an optimization problem with the same KKTs? That's my question. Reverse KKTs, how can we reverse KKTs? I'm not sure we can do some inverse engineering and from KKTs we end up to an optimization problem. Okay, I think you got the question. For answering this, please read chapter 4 of Stephen Gabriel's book. The book is online. I already uploaded it on DTU Insight. Please learn about principle of symmetry, and also learn how to derive a Jacobian matrix of an equilibrium problem. You need to derive a Jacobian matrix and check if it's symmetric or not. If it's symmetric, your equilibrium problem has an optimization problem, has an equivalent optimization problem. But please learn and explain tomorrow how to derive a Jacobian matrix of an equilibrium problem. So you can read chapter 4. Also, you can read theorem 1.3.1 of the book by Fassini and Zhang Shipeng. That book is also uploaded on DTU Insight portal. Is it clear? The question, is it clear? Good. The last question that you answered, some of you already asked. We have a Nash equilibrium problem. I'm not saying GNE. For GNE, it's very hard to explore the solution existence and solution uniqueness, unless for very specific GNEs, like GNEs with shared constraints, or for some kind of GNEs that we call it variational equilibrium, we can explore existence and uniqueness. But in general, for GNE, it's really hard. But my question is for NE, Nash equilibrium, how we can check the existence and uniqueness of the solution. Okay. So for existence, it's easy. You will find easily. But for uniqueness, you need to read a bit more about monotonicity property of the game, and to check how we can know that a game is strongly monotone by checking the Jacobian matrix, the matrix that you learned in exercise 3. If you are very, very, very interested, you can also read about degree theory, which is a more complex theory to understand the uniqueness, the solution uniqueness of an equilibrium, of a Nash equilibrium. So here in exercises, I provided you a lot of keywords and some references. So yeah, just go and read and search what you can do. Yes, yeah, that's it. So maybe, so we have a question. Do you have any recommendation from where we could find data for our projects, price, capacities, etc. instead of IEEE? You can go and check, you can get the real data. You can go Nord Pool website, you can go PGM website, New England website, and you can get some real data if you like. Yes, exactly. Yeah, or we can go Elia website in Belgium or Enzoe website. You can get a lot of real data from those markets. If you want to pick gas or hydrogen, well, for gas system, I have a test case of 12 nodes. I can share it with you, so you can write me an email. But for hydrogen, I have no clue. Good. Any other question about exercises? Yeah, also I have a passcode for MCP that also I uploaded that code on DTU Insight portal. So also you can check it out there. Well, I can stop sharing. Yeah, thank you so much for the lecture. If you don't have any other question, maybe we can conclude and then see you tomorrow. Thank you. Bye-bye. Bye.